Hello, everyone, and thank you for joining today's webinar. We're going to give everyone just a moment to join, so I'll ask that you'll be patient for about a minute. I can see numbers are coming in, and we just want to give everyone an opportunity to hear the full presentation. For those of you that are just joining, we're giving everyone just a moment to join. We'll get started shortly. Thank you for your patience. All right, I have about a minute after, so we're going to go ahead and get started. Thank you again for joining today's presentation. My name is Robin Carr. I'll be your moderator for today's event. Thank you again so much for being here. Before we get started, I have a few housekeeping items to go over. If you lose audio or video, simply exit GoToWebinar and rejoin. That will resolve about 90% of any audio or video problems you may have. There's a chat feature in your menu that you can use for general questions or assistance, technical assistance of any kind. If you have a question for our speaker today, please place those in the Q&A section, so that I'll be able to see those and present those to Stephen if we have time at the end of the presentation today. We're going to hear from Stephen, and then we'll go directly into Q&A session if we have time. If we find that we don't have a lot of time for question and answers, I'll try to get at least one or two in. The others I'll forward to Stephen so that he can respond directly to you via email. So our presenter today is Stephen Hudson. Stephen is a director of professional services here at Fluke Reliability. Stephen has over 30 years of vibration analysis expertise, business development, product and service delivery, and scalable operations. He focuses on efficiency and promoting internal collaboration for consistent results, client partnerships, and brand quality. All right, so you're here today for slow speed and early fault detection, how to solve. Stephen, take it away.
Thank you, everybody. She's already kind of introduced me, but I'll just jump right into the first slide. I have a submarine background, and I've spent 36 years after that in the industry of predictive maintenance. So I joined Azima DLI in 2010, and I have been director of the operations services here since 2018. Personally, I've got 11 grandkids. I enjoy woodworking and auto restoration, so that's what keeps me busy when I'm not doing this kind of work. So we definitely have a lot to get into. This is a kind of a long and technical topic, so I hope everybody is ready for that, and we'll get moving right into it. Today we're going to be discussing just slow speed techniques and our impact detection algorithms. It's based primarily on industrial piezoelectric accelerometers. If we have time at the end, we may dabble a little bit in what we're finding with the MEM sensors as well related to that. Slow speed machines, real quick, I'm just going to define them. For us, we define slow speed machines as shafts below 60 RPM. Typically, when we get below 60 RPM, our diagnostic repeatability becomes much less ability to be repeatable, and we think it's a reduced ROI on those assets. So I think that's one of the reasons this is a hot topic for a lot of people, and there's a lot of facilities and a lot of verticals that have a fair amount of slow speed machines, so we try and work towards those machines and always get better. So we are in kind of a continuous improvement process around slow speed, but it certainly has a whole amount of process related difficulties that we're going to get into. One of the things that I want to just put out right up front is if I can influence any of you on anything, it's going to be that you walk away remembering that demodulation is just a compression technology. There's nothing really else. I'll start with that. We'll get into it. So back to slow speed. One of the reasons slow speed machines are difficult is the time it takes to collect the data. It's very long data capture times. It's highly susceptible to speed variation. When it comes to the sensor, since we're talking primarily piezoelectric, it requires a very low sensor, it creates a very low sensor output. It requires a large seismic mass if you're choosing to go into low frequency or specialize a particular machine into low frequency. And it requires a long settling time, and then we don't recommend using analog integration. And then the last piece is kind of the other thing that we use, the third leg on that stool is that we use impact detection. Our algorithm is called impact demodulation, and that's pretty much the bulk of this discussion today is going to be about that. So sometimes, and we certainly find this quite a bit, and even very recently we had a case where impact detection was the only indicator. We saw nothing in the regular spectra and the regular time waveforms. We only saw it in the impact detection algorithm, usually paired with some sort of oil sample changes, some sort of metal in the oil. Those two oftentimes in a very slow gearbox is our only indication. This is just an example of what I mean when I say slow speed machines require long data capture times. So it definitely requires more planning. If you're doing portable data collection, you're going to spend a long time at the machine compared to a standard 1800 RPM machine. The example here given is an 1800 RPM machine and a low range spectrum and time waveform with a max frequency of 300 Hertz would be the example. And that takes about 13.3 seconds to collect that entire sample, 4 averages, overlap, all the typical things. The same range in a slow speed machine, and again, this would be 60 RPM, and it goes much longer if you go slower than that, but in 60 RPM, if we go for a Fmax of 10 Hertz, is going to take 400 seconds for a single sample. So single location on a machine, much, much longer. So that's challenge number one. Data collection times are much longer. That also affects wireless sensors because they don't have the battery life to sit there and collect data for these long amounts of time. So kind of a separate topic, but it is one of the factors that's considered in the low frequency ability of wireless sensors. One of the other issues we have with low speed machines is if there are speed changes. This is just an illustration of what it might look like. Let me get my pointer on here. What it might look like if we had a speed variation. Again, this would be the time series data. Constant speed would look pretty sinusoidal, for example. And if the machine were varying speed up and down, for example, we might get something like a frequency modulation or any sort of speed change during the data collection set is going to give you a smeared spectrum. And that oftentimes will make the spectrum unusable, unable to diagnose specific faults. And so again, any speed change during data collection is a problem. This can be a problem with things like downcoilers, uncoilers, and paper mills, big machines like that are known to change speed during the data collection process. So oftentimes that requires extra features in an analyzer, such as an online system, order tracking features. Some of these things are built into portable data collectors, including ours, but they're still very difficult to actually use in application and require many extra steps. So we'll move on from that. Now, accelerometer selection, the other factor that I talked about is the very low signal that you're going to get out of an accelerometer at low frequency. And again, when we're talking accelerometer, it's a direct acceleration measure. It's not a derivative. So it's got a very high dynamic range and frequency range an accelerometer does, but at the same time, it has a very low voltage output at low frequency. And just in an example of this, I've charted out if we were to have a signal that would be equivalent, most people look at their data in inches per second and velocity, essentially. If we were to chart that out as a voltage at different frequencies, that same amplitude at 6,000 RPM down to 60 RPM. At 6,000 RPM, that's 0.0115 volts. As an example, at 60 RPM, a 60 RPM shaft, to have that same level of vibration in the spectra is going to be 0.000115 volts. And so on. As we get even slower, that voltage steps down. You can see it's a linear it's a linear relationship, but you get to a very small voltage. Now, this was a big problem with us early on. Again, I've been in the vibration business a long time. It was a big problem when we had 12-bit analyzers, and we only had 4,000 voltage steps in 12-bit analyzers. As today we're into 24-bit analyzers, they can resolve 16 million steps in voltage. So they have a much better chance of resolving those low voltage. But again, it does still present that problem that these amplitudes that people want, if they want to know the rotation rate of a certain slow speed shaft and they want to see it in their vibration spectra, it definitely creates a very low voltage and very low signal down there. So the other important factor with low speed from our perspective is both the gain and the seismic mass in the accelerometer. Oftentimes we can go to a pretty good low frequency with a standard accelerometer, which most people would just consider an off-the-shelf or even our triaxial accelerometer that is 100 millivolt per G. I don't encourage people to use 500 millivolts per G. I think since we have 24-bit analyzers, that's no longer helpful, and I'll kind of explain why. What I do think is important is if you have a large gearbox and maybe an online system, I would recommend going to the sensor manufacturers. In this case, CTC gave us this photo of 3 of their sensors. They're all identical in most aspects. They're identical in the fact they use a similar amplifier. They're all 100 millivolt per G output, so they have the same output sensitivity. But the big difference you see here is the seismic mass. And it means both the frequency response is different and their ability to do low frequency measurements is different. And the one on the right with the large seismic mass actually means that we get a mechanical amplification of that signal before it ever even goes into the amplifier. So that is really the right answer. This is typically the sensor that we use or recommend, or a variant of this for low speed applications with online systems. So the two factors that really affect low frequency are the electrical noise of the internal amplifier, and that has definitely been improving over the years, but it's a fairly fixed amount. And then again, that mechanical gain, how big that mass is going to really help you improve the signal before it ever hits the amplifier. Having an amplifier that amplifies to 100 millivolts per G or 500 millivolts per G is really nothing other than just a different amplifier, different electronics. There's no difference in the actual signal. It's just taking it to a higher voltage. You know, CTC described this as basically leaving the city, having your radio cranked into your favorite radio station, and the static starts increasing, so you just turn the volume up. You get more static along with more music, but again, the static's still there. It's not going anywhere. When you increase the seismic mass, you're actually reducing the static. You're actually reducing the amount, you're improving the signal to noise ratio. So that's the important part. And again, I've already mentioned, I think our experience is the 500 millivolt per G is unnecessary with 24-bit analyzers today. And we find a big downfall to 500 millivolt per G. Because they have such a narrow range, they're easily swamped, particularly on gearboxes, which have high frequency noise in them. And that high frequency noise will often swamp out that 500 millivolt per G sensor, and you don't even know it. You're flying blind. You're not getting any real data out of them. So we avoid their use pretty significantly in gearboxes. So again, I think the typical practice for the last 20, 25 years has been 500 millivolt per G, but I think today it's really unnecessary. And again, it does create some harm. I want to use this slide to give you an idea of what I mean. This is a big data set. This is about 50,000 machine tests that we had over 4 months of data in a large business. All of this data is collected at 100 kilohertz and above, so it's a very wide range of data. So it captures low frequency noise, high frequency noise. And if you notice, about 10% of that, about 10% of the data coming in exceeds the range of a 500 millivolt per G sensor, which is typically 20 Gs. It's pretty narrow. As a matter of fact, 130 of these tests exceeded 100 Gs, and we even had one test that exceeded 200 Gs. To be fair, that 200 Gs is outside the linear range of our sensor, but it still was able to measure it So it is probably plus or minus 10% on that one. So people are often surprised how often or how much data comes in that is kind of above the exceedance level of those 500 millivolt per G sensors. So and this is kind of my last slide on this. I'm just saying that, you know, a 500 millivolt per G does amplify the signal and the noise. It amplifies both. And sometimes you get a gain out of that, but that's really with older analyzers. It gets a very low range. It's usually typically around 20 Gs. That is the full range of the sensor, certainly the full linear range of the sensor. We find that going with high mass 100 millivolt per G sensors is advantageous. The 24-bit analyzers that we use, definitely the amplification is redundant. We don't really gain any benefits from that. So we use standard amplification, and we get a very robust frequency or amplitude range. So again, seeing the previous graph that we just looked at, you know that a lot of our data lives above 20, above 30, and oftentimes above 100 Gs. The last factor in slow speed accelerometer selection is going to be the time constant. This is usually controlled by your sensor manufacturer. If you ask them, they'll tell you, they'll be happy to tell you more about this. That CTC sensor I showed before, this would be a subtle difference in that sensor as well. Not just the higher mass, there is a second piece of this, which is the resistance capacitive time constant of the sensor. And basically, a high time constant gives you a better low frequency response, but you suffer from a really long settling time. So they aren't usually well suited for a walk around system. Otherwise, you would be standing at the machine for 30 to 50 seconds waiting for that accelerometer to settle. When you attach the accelerometer, it certainly disrupts that signal. Oftentimes will overrange it, and then you have to wait for that sensor to settle out. Anybody that's doing data collection has seen ski slopes and things like that. So bottom line is a good low frequency sensor would have a long settling time, both from temperature and or shock, if you were using it for portable data collection. So we compromise, right? So most accelerometers compromise between that low frequency response and that settling time. So it is a built-in factor of the accelerometer, and it has to, again, to do with the output circuitry of those amplifiers. All right, we're going to move directly into probably the biggest part of this presentation, which is impact detection. This is kind of our last and probably becoming more and more important detection method for helping us in slow speed. Obviously, it helps us in high speed machinery as well. It is not. It doesn't solve everything, but it certainly gives us a better view into what's going on in slow speed machines. And again, we just recently had a case where we had a large gearbox, and the only indicator we had of failure was the impact detection tool. There was nothing, and there's no indications in the regular high range or low range spectrum. Before we get into it, this is where we get a little bit more technical. So for some, this is going to be fun. For some, this may be, complete foreign language, and I'm sorry for that, but there are a few kind of important factors here that I hope to impress upon everybody as far as why we think this impact detection is superior and why it works, and a little bit about the background on it. The biggest thing here that I want to walk away with is, again, we do have to talk about Nyquist criteria, what that means, and why it's important to detecting impacts. So we'll start by kind of defining a little bit of that. From a concept standpoint, I would like everybody to know that, there's kind of two different kinds of vibration. If you study vibration, there's what's termed as whole body vibration, and there's stress wave vibration. These two vibration types really have some sort of crossover, and it's really hard to define that frequency because it's going to be different for every machine. But you can think about whole body vibration as any vibration that makes the entire machine rock or move, or, again, pretty easy to visualize what that kind of vibration is. A washing machine that's jumping around, that's whole body vibration, right? However, at the same time, you have stress wave vibration, which really has more to do with high frequency vibration, which instead of traveling as whole body vibration across the entire machine, it will travel more like waves in a pond, ripples in a pond, right? It will travel across the metal or the material in that manner rather than moving the whole thing. And while we detect both with our accelerometers, they can be meaningful in different ways. So the interesting thing about that is that roller bearing faults in particular, and I should say gear faults, those kind of faults really, detection of those faults fall into both of those categories. Oftentimes, early detection of those faults starts out up here in the high frequency, and then as the fault progresses, it will typically also begin to show up in the lower frequencies, and then eventually usually near the very end of the fault, usually late stage fault, it will show up as whole body vibration. This is oftentimes why we refer to like low resolution wireless sensors as hand raisers, because they won't catch any of this early detection. They'll only catch it just before it fails, which is when we start seeing those kind of failures in the low frequency ranges. A little bit about Nyquist criteria. Just real quick to define that. Nyquist criteria, for those of you that aren't familiar or those that have, it's been a while since you looked at your vibration books, a repetitive waveform can be correctly digitized and reconstructed, providing the sampling rate is either 2 times the highest frequency to be sampled, that's really difficult to do, or 2, the sample contains no frequencies higher than 1/2 the sampling frequency. That's 2 different ways of saying the same thing, but it's easier to attain removing any frequencies that are higher than half the sampling frequency, and that's usually the strategy that's used, right? With accelerometers, I'll remind everybody, we know what frequency response curves are, but just because a sensor only goes to 5,000 hertz frequency response, that's just its linear range. I'll promise you it will detect things at 10,000, 20,000, 30,000 hertz. All that data will come down those wires into that digital data collector, and if you don't properly filter for this, you'll be in trouble, and we'll talk a little bit more about that. Again, making the point, if Nyquist criteria is not adhered to, the resulting digitized time series data will contain a distortion known as aliasing, otherwise referred to as a false signal or fake signals in our data, and we have to stop that at all costs. I got a visualization here. This is an example of aliasing in video. It helps some people kind of better understand what I'm talking about when I talk about aliasing, and in this example, you're going to see a helicopter rise and it looks like the rotors are not moving. Everybody knows that those rotors are moving. If you stuck your hand through it, you would lose your hand. It's a very real thing, but this is, again, just a quick visualization of what happens when aliasing is allowed to be contained within your data set. If we allowed this in a vibration data set, we would see a very large peak at zero RPM. That would be meaningless. Again, it creates false frequencies that have nothing to do with the actual running condition of the machine. And for us, it would lead to false diagnostics. So we have to prevent this kind of data, this kind of alias signal from getting into our data. Super important. Strategies typically are, again, this is going back 30, 40, 50 years when digital data collectors first came into being. And there are strategies even other than what I'm listing here, to be fair. But a couple examples is I know early data collectors use anti-aliasing filters, which were banks of RC filters on the input, on the analog side of the data collector, which would basically filter out any samples prior to the analog digital converter, and it would remove any of those frequencies that were above half the sampling frequency. If you're sampling at 1,000 hertz, it's going to remove any frequencies above 500 hertz, and that prevents that phenomenon. The other strategy, which doesn't work so well in vibration data collection, unless it's done at a very high sample rate, is oversampling, which means you just sample super fast, well above any frequencies that would possibly be in your data set. And again, if you're not sampling, even if you sample at 200 kilohertz, there are opportunities, certainly in certain machines, that you're going to get frequencies that are above 100 kilohertz, and again, start to destroy your spectrum with these A-list signals. So just be aware, these strategies are in place in your data collector. They're there today, and as long as they're well understood and well implemented in your digital instrument, it's all behind the scenes. You're not even really aware this is happening if you haven't previously studied it. But it is super important to make sure these signals are pulled out of the signal before you digitize it. Otherwise, you get strange peaks in your spectrums that you're trying to identify that have no meaning to the actual running machine. We're going to talk a little about what an impact is. Impacts are generally those events that I discussed, create stress waves across the machine rather than machine motion. Sometimes they can cause both. Sometimes if they're big enough and depending on the frequency of them, they can create a little bit of machine motion, but they'll generally create stress waves. They're characterized by short duration microsecond events, and they're not visible in standard time series data sets. So if you're not sampling fast enough, you're not going to see them. Why not? The anti-aliasing filters will pull them all out before you ever get a chance to see them. They're doing their job. This Nyquist criteria thing I talked about is really why we don't see these things, because they're pulled out of the data. And I'm going to give you several examples of that. Just general purpose, a single impact event in time data looks something like this. It is a spike with a ring down. You can think about ringing a bell. That's very commonly what you would get here. If you struck metal, you would get these kind of impact events. And this is really what we're trying to capture, because we don't see this in normal data collection sets unless we're sampling very, very fast. So let's talk about it. This is an example of actual data. If you notice, this is a very, very short, 6 milliseconds. It's a very short data set. And you very clearly see this impact event that happened. Very interesting. You notice on the amplitude, it's plus or minus 35 Gs, so it's over 70 Gs in impact amplitude, very high and very noticeable. So this is really great. This is what we're trying to capture, and I've got a picture of the bearing behind it. This is the actual defect that was causing this particular impact. The interesting thing about this data is the ring down frequency. If we look at the frequency of that ring down, it's 13.5 kilohertz, so 13,000 hertz, well above what most of us are sampling in most of our portable data collectors. The total event period is only 1,000th of a second, so it happened really, really fast. And those two things are important, because normal methods, even legacy demodulation methods, have a weakness here and an inability to capture these really fast events. The other point is if you're going to use legacy methods, both regular data collection or legacy demodulation, the entire event period must meet Nyquist criteria, or those anti-aliasing filters will strip this entire event out. You will not see this in your final time data. It will just simply disappear. Little bit more about what is important. I mentioned the 13.5 kilohertz ring down, spike and ring down. The 13.5 kilohertz really isn't important to us. We don't care what the ring down frequency is. What we do care is the event, the period of that impact, because how often we see that impact can be meaningful to us. If it's random, it could be lack of lubrication. It could even be cavitation if it's a pump, for example. If it's periodic, oftentimes it will be related to a bearing fault frequency, a gear frequency. So again, the event period is what we're interested in, not the specific ring down frequency or the event duration. Both of those are meaningful in a signal processing standpoint, but they're not meaningful from a diagnostic standpoint. This is a different look. Actually, this is that same data I showed you with the impact, but now we're zoomed out a little bit. We're looking at, what, 0.5, 50 milliseconds. Anyway, as we zoom out, now I'm going to make the point of what we really want to know, which is we notice here, compared to the revolution on this machine, we get double impacts each revolution, and that was helpful as well. But the period of this event, in other words, how often it repeated itself, was one revolution of a high-speed shaft. This was a gearbox, and we were getting a set of impacts every revolution of that high-speed shaft. So that was the meaningful information that helped lead us to determine what the cause of the fault was. So again, meaningful information is how often these impacts are happening. There's a statement that's floating around out there. I've seen it in textbooks, and it's basically that bearing faults are difficult to detect because they produce tiny signals that are hidden in the noise floor. Our experience is that this is completely false. This is a falsehood. This is not really why we're having problems detecting these signals. And that's, again, a big thing I want to impress upon everybody today. This isn't about some special signal processing method that will bring things out of the noise floor. This is really just about taking a different tact when it comes to, again, understanding Nyquist, understanding that these signals exist. They're coming down the wires from our accelerometers, and our digital data collectors are completely ignoring them. How do we stop that from happening? This is the common idea, which is, okay, and this is a real set of data. This is a set of data that I'm going to show you in two different forms. I'm going to show you in kind of what was the traditional form. This one was sampled at 6,000 hertz. Pretty typical for a high-speed machine, 6,000 hertz Fmax. And then we integrated the data. You notice it's in inches per second. And what you can see in the data is you can see maybe there's some potential impacts events. You can see how that might be hidden in the noise floor. But that's really because we didn't sample it correctly, and we're not looking at it correctly. We should have never integrated this, and we should have sampled much faster. And so if we sample it at full sample rate, we see a completely different picture. This is not integrated. It's 180 Gs now. What the heck? It was what? I'll go back here. It was less than a G. Yeah, less than a G. And now we sample faster and we don't integrate, and we're seeing 180 Gs. This is almost the full range of the sensor. So this signal was on the wires coming from the accelerometer, and we were ignoring all this, right? So oftentimes with our sampling techniques, we throw away the meat and potatoes and we're just left with the broth. And we need it all. And so that's what we're trying to achieve here, and that's what I'm trying to kind of talk us through here. Impacting often dominates the raw data. So, and if we take a look again, we sampled, in this case, we sampled at 16 kilohertz, or that wasn't our sampling rate, that was our Fmax, right? So that times 2.56 would give you our sampling frequency. But you see here again, what appears to be periodic impacting, and it's dominating that time signal. So this was a very important fault, and it was very late, and it was lucky to have been caught. This is several years old now. This is when we were first employing our impact tool. And it was very important to know because the customer immediately tore this machine down, and it was in late stages of failure. And we wouldn't have seen it, or we would have probably qualified this as a moderate fault given that original data and just a regular data set. So again, the look is very different. And it's important that you understand that it's in the data if you'll allow your analyzer to actually see it. So why is it difficult? What makes this difficult to detect? I mean, hey, I just showed you, hey, I can see it real easy. I just got to do a couple tricks. What's the problem? Well, one, it requires a very high sample rate. I mentioned that already. We have, in a couple of test studies that we've done, we've verified that really you need to be sampling at least about 25 kilohertz, usually an Fmax of around 10,000 hertz to capture most of it. We still feel that that is sometimes low. We prefer to sample at 50 kilohertz and above. And I'm sorry, 40 kilohertz sample rate, usually a 50 kilohertz bandwidth. So our Trio typically uses 100 kilohertz as a sampling bandwidth or sampling rate. Sorry for confusing those two. I'll probably do it quite often, but and then so our Fmax is 40 kilohertz, and it requires a long sample time. we need to provide adequate low frequency resolution. So essentially, if we sample really fast and we sample for a really long time and we get at least 15 shaft revolutions, that's the thing that really applies to slow speed machines. If you have a 60 RPM shaft, you'll need at least 15 seconds of sample at max sample rate. It gives you a 15 million sample, or yeah, it gives you a very large data set. And so that's the deal. When I talk about this being a data compression technology, that's exactly what I mean. These result in very large data sets. The data set for just our standard trio sample is 500,000 samples that we usually start with before we run our algorithm. In our online system, it'll be 14 million samples. That will give us a couple of minutes, more than a couple of minutes of data sampling time. So what do you do with 14 million samples? Where do you store that? And if you're taking that every day, you're going to have well into the terabytes of database size. So this has always historically been the problem, is how do you deal with these super large data sets? Let me give you an example. Standard sampling here, probably for an 1800 RPM machine for us, 300 hertz, 1600 lines. That gives us a typical separating frequency. The resolution of the spectrum gives us roughly 33 CPM as separating frequency. To maintain that separating frequency and to sample at high frequency rate, in this case 40 kilohertz bandwidth, is going to require 550,000 samples. Very large data set. Let me give you one more example of this, but in a lower frequency. In this case, we're doing a 30 hertz sample on a slow speed machine, say a 60 RPM machine. We get a separating frequency, right? The resolution that we want to be able to see to resolve peaks, 1.7 CPM. If we do that at our max sampling rate, that gives us 10 million samples. So you can see we quickly get into needing a data compression methodology. And that's pretty much how we handle our impact DMOD, is as a data compression methodology. And to be honest, all demodulation methodologies are a form of data compression. That's really all they're doing for us. They're not bringing it out of the noise for you. They're just finding a way to compress it differently. So move on here. To give you an example, this is a data set taken off of a compressor, and it was a compressor bearing fault. And the purple time waveform that we see here was a standard data set, 3,000 hertz, pretty standard for us for a high range on a compressor like this. And we were only seeing 1.8 Gs, and we stored, in our typical 1600 line is going to store 4,096 samples in the time data set. Pretty standard and pretty manageable as far as database size. And then you see the blue time waveform behind it, and you can definitely see it's much higher amplitude. We got about 14.1 Gs peak to peak, and we see that, and we're like, wow, that's really what I want to see. That's really what I want to analyze, because it has all the information I need. Well, this particular one was sampled at 25 kilohertz, and we stored about 25,000 samples. Not super huge, but still very much larger, and makes database management much more difficult. Our impact DMOD algorithm, on the other hand, gives us that same result. We get again, we'll look at why it looks like more like a spectrum, but it's just a rectified time data set. We see clusters of 3 peaks every revolution, and it tells us it wasn't actually every revolution. This one was cage rate. We saw these clusters of three peaks at cage rate, so we knew this was a very severe bearing fault. And if you notice, our impact DMOD max value is roughly or pretty accurately equivalent to the actual peak-to-peak value in a raw time data set if you sample it fast enough. So that's what we're trying to do here, is we're trying to maintain that amplitude. And the nice thing is we sampled at even a higher sampling rate. We had a 40 kilohertz bandwidth, but we're only storing, again, back to 4,096 samples, very manageable in a database. So this data set gives us what we need, and compresses it down to something we can use and store in a real database. So this is another example, very, very similar. You see here that we have In the regular data, much higher, 29 Gs, pretty impressive. I think we were probably going to see and report a problem on that. But when we actually sample it at 40 kilohertz and store those 25,000 samples, we see that it's 147.8 Gs. And because it's such high Gs, we need to act immediately. This machine is in real distress. So we move quite quickly on it. Our impacting data, now this is a good overlay. Again, we're looking at the same half a second, the same half a second worth of data here, and look, again, the peak or the max amplitude that we're seeing here is 144 Gs compared to what was in the other data set, 147 Gs. So essentially, there's a slight difference in time, and the amplitudes are essentially the same as if we sample really fast and store a big data set. So again, it's data compression, allows us to maintain those amplitudes and maintain a look at what those frequencies are as well, but doing it in a very compressed manner. A quick look at legacy demodulation, and again, this goes way back. Many modern data collectors are doing it different. Different companies are approaching this in a different way. This is kind of the, again, very legacy, basic overall, how we did demodulation in the past. We typically signal high pass filter. We still do that today. That has one function for us, which is basically to remove the whole body vibration out of that time data so that we know that everything we got left is stress wave related. So signal high pass filter. 2, we rectify the signal. Again, this is legacy demodulation, and this is how our data collector used to process this. How we doing for time? We rectify and force all those peaks to be positive. And then this is the weakness of legacy demodulation. We signal low pass filter, we envelope it. The problem is this envelope still has to meet Nyquist criteria for whatever the final sampling rate that is required. So it still has that vulnerability of stripping out anything that doesn't have a long period of impact. So we'll capture some impacts, but it doesn't capture all impacts. Then they digitize the signal, and then they perform an FFT so that, again, you can determine what the frequencies are if there are discrete frequencies in that data. Again, it requires a low pass filter that must meet Nyquist criteria, and this is just giving you an example that really, because it's going through that low pass filter as the final, as one of the final steps, that filter setting depends on what you're asking. If you're asking for a 200 hertz final bandwidth, then it's going to be filtered. That means everything above 100 hertz is going to be filtered out of that final data set. So even if it captured the individual, shall we say, ring down frequency, if the entire event period doesn't exceed 100 hertz, and that first example I gave you was 1,000 hertz, it's going to be filtered out of a standard demodulation. So you still may not see it, and this is particularly true in slow speed machines. So Azima DLI impact detection methodology. We'll just talk about what it is. It's a very different process. Some people in the past have called it digital demodulation. Essentially, it is a sample and hold methodology. In our case, we look at basically the max values in a particular bin, both the positive max and the negative max value in a bin, and then we downsample that to a much slower rate. It doesn't then require any additional anti-aliasing because the methodology more or less has that Nyquist criteria built into it, shall we say. So by default, it is immune to those low pass filters that would need to be in the final step. So again, showing here that we evaluate extreme values in that original raw data. So we sample it very fast. We buffer that 500,000 samples, for example, and then we run this algorithm which evaluates those time blocks and then decimates it to a new approximate value. And then it just continues. So it continues through a time data set. Sometimes it'll be 10 to 1, sometimes it'll be 1,000 to 1 decimation. So it reduces the sampling time significantly so that we get that compressed data set while maintaining those max amplitudes. Because again, the two things we're interested in is the amplitude, which tells us severity, and the period or the timing of those impacts. And this preserves both of those items. So that's why this methodology is a little bit different. I'll play that one more time just to kind of let it sink in a little bit. Now, again, so let's talk a little bit about the steps we take. And, you know, that's the algorithm. What steps do we take to actually get the data? One, we sample really fast. I mentioned in our trio, for example, we'll sample up to 500,000 samples. We'll sample it at 100 kilohertz, meaning 5 seconds worth of data, 100 kilohertz. We get 500,000 samples, and we digitize that. So, and that is passed through that an initial RC filter. So it is, this does meet Nyquist criteria, bottom line. And we digitize that. And this is just an illustration of what that might look like. Some impacts along with maybe some sinusoidal data. Then, as I mentioned, we pass it through a high pass filter. Just like in the old methodology, we like to remove machine motion data, basically whole body vibration, from impacting or stress wave based data, so that, for example, my analysts know that if it's got a high 1x content, that doesn't have anything to do with balance. There's something loose, there's something causing an impact once per revolution. Then we run it through our algorithm, and that's that piece that, again, downsamples it to a much lower frequency space so that we can compress that into maybe 4096 samples and store it. But it preserves both the amplitude and the spacing of those peaks. And then the last step is we do create an FFT in our portable devices and in our online devices so that we can then do spectrum analysis. And that's not even as necessary. It's not fully necessary. It's just helpful to the analyst to be able to go in and determine what those frequencies are. Some advantages: there's no low pass filter attenuation. It just isn't needed. It retains a maximum waveform amplitude, as I mentioned, regardless of whatever your final Fmax is. If you want to choose a 500 hertz Fmax or a 50 hertz Fmax, you're going to still have the same maximum values. Simple filter selection. It doesn't require a whole lot to know about filter selection. It's pretty simple, and it's robust. If you get it wrong, it's still going to give you good data. But again, you can use the advantages if you do have some filter settings. It does not rely on knowing a resonance peak on a sensor either. So again, our system altogether uses a blocking system. We don't use magnets. We have a very well-known frequency response, and we track this statistically, and we track it based on each and every location. So each and every location gets its own alert set point based upon where it has been historically. Setup tips, not really super important, but we do use units of acceleration. We don't integrate this, obviously. We try and capture a minimum of 15 shaft revolutions. If you approach me with a shaft that I can't get quite 15 shaft revolutions, we'll make a determination. 10 is usually going to work, and right, so there has to be compromises at times depending on what instrument you're using to try and capture what slow speed shaft. And the reason for 15 shaft revolutions is we're trying to capture a minimum of roughly 6 cage rate revolutions so that we make sure we get enough data. But again, all of those things will become evident. Number of revolutions in a waveform, again, this calculation is available. It's pretty simple. And then the other thing is we only do one sample. But really, the sample we need is the time data, not the spectrum. So we don't do an average spectrum. So we do one average or no averaging here. We use the lowest filter setting. I mentioned about the filter settings. We try not to overlap the desired Fmax with our filter setting, and we use the inline axis. Again, we're a company that does primarily triaxial data collection, so we always stay in line with that blocking system and only track that inline. We could get a little bit more into that if we had more time, but we're tight here. Analysis tips. We review the time waveform first. This is where it turns it around for all vibration analysts, right? All vibration, I should say all. Most vibration analysts are used to doing spectral analysis, looking at the spectrum first, determining frequency. This tool turns it around. You learn the severity, and a lot about the information by looking at the time data first. So we always defer to the time data on this. Maximum peak value determines severity, and again, that's based upon relative peak value. This gearbox I talked about recently, it was very clear that it was started at a very low level and escalated over time. So we learned a lot about how that works and are continuing to learn a lot. Again, this tool is about 10 years old for us, and we are always trying to get better. We compare it to other like machines, but really we've evolved to, as I mentioned, using statistical averaging to help us set that set point, determine on the individual location's history. From there, you determine the waveform content, and you basically determine, I gave you some examples, they'll oftentimes look very periodic, and from there you can go to the spectrum and determine what the harmonic sets might be and really get to it. Random impacting, something like this where maybe you can't determine if it's periodic, maybe it's not. This is pretty high, but typically random impacting indicates metal friction. We'll see a dry bearing. This is typically what we'll get out of that. Another case where we'll see this is pump cavitation. So we have to be cautious when it's on a pump. We recognize that it again could be cavitation, and that's still meaningful as well. Got to figure out why that pump is cavitating and solve that as well. Periodic impacting, again, this is the time data set here on the left. You can see, just to the eye that it's very periodic. The impact rate usually indicates the faulty component, and you review the spectrum. In this case, it was 3.11, which is a outer race fault for an 8-roller element bearing, very clear in the spectrum. So those are just kind of the analysis tips. We're doing okay on time here. I've got a couple of examples that I'll go through, and then we'll see if we have see what we have after that. So in this case, a 2,000 horsepower vertical motor. This data set is old. If you guys notice the dates, this is the very first time we used impact DMOD on a set of machines and found this particular issue back in 2012, I think, when we first started using our tool. And in this case, we're looking at regular data here. This is just normal data collected by our data collector. And we noticed that there were some bearing tones, harmonics, sidebands. The diagnostic system kicked out a moderate fault. So it was a known potential fault. But what we found interesting here is that our standard time waveform only had 4.3 Gs. Nothing really significant. But when we took the impacting data, we immediately noticed that we were actually, with that high sample rate, we noticed we were at 52 Gs peak. Very different picture, very, very different picture. Looking at the impact DMOD spectra, we noted that there was periodic content at 6.9 times motor speed in this case, and it was a ball pass outer race tone with harmonic. Very, very clear, very, very high impacting. So the company, the customer in this case, scheduled it for replacement, and it took some months to get this done. So they had to run in this condition for a period of time. So they continued to monitor it, and turns out it was severe electrical fluting. You can see a zoom in on the right-hand side of the outer race where that electrical fluting was. So again, it was a little bit underwhelming in the regular spectra and really didn't show what the severity really was. And then the last thing was I wanted to show you a before and after of that same time data taken on that same bearing before and after repair. So again, you notice the time difference is 5 months. So it took them a while to get it repaired, but once they did, it was the baseline data on this thing was less than 5 Gs normally. So it was a good catch. I'm going to give you another interesting example because this particular one is I'd say it's a diesel engine. It's a combined fuel type engine that was running through a gearbox, through a speed up gearbox to a generator. And surprising enough, we can and have successfully used this tool in certain diesel diagnostics. Again, diesels come with their own amount of built-in impacting, different discussion, but it does prove that the tool can be effective in that scenario. And in this one, I wanted to show you that over, again, several months period of time, the progression of the impacting that we saw on this machine I think I have the values here. Yeah, so in January it was 27, it escalated to 33, 67, and by June this thing was 80 Gs. This is actually also the very first example I gave you of that 13.5 kilohertz, that ring down that I used. This machine gave us some really good data to use for showing this. And in the spectrum, when we looked at the impact spectrum, we had indications of an inter-race bearing fault. So we had BPI, we had side bands, let's see here. So we also had rotation rate harmonics, so there was some looseness associated with it. And again, remember, what's in this spectrum is not actual rotation rate. It is not whole body vibration. This has been, all that's been filtered out. So this is all related to high frequency vibration. And it showed both inter-race tones with side bands, and it showed rotation rate. So there was a significant amount of looseness in this bearing as well. And so the gearbox high-speed shaft basically had an inter-race fall. I have a little bit more I could go, but I think it'd be best right now to probably end this. I really only, I can talk a little bit about MEM sensors. I will say that we've had success with this tool using it in MEM sensors. That was a little bit of an unknown. MEM sensors behave very differently, but we do use the impacting tool in our MEM sensors, and particularly our wireless sensors, with success. And there is, and particularly because we've taken the approach of using a statistical average to track that. We find that to be very useful, and our wireless sensor does sample at that minimum sampling rate to this technology. Other than that, I'm going to turn it back over to Robin to see if we have any questions.
Thank you, Stephen. We do have a couple of questions. My first question is ultrasound much better to be used in a slow speed equipment than vibration analysis?
I don't think it's much better. I would say that the results are roughly equivalent. So it depends on the ultrasound that you're using and how you get your results. Again, it's two different approaches, but both of them use this high frequency data approach. One of them is using obviously contact spectral analysis and in the same instrument that you're doing vibration analysis in. But I won't discourage people from using ultrasound because it potentially can get very, very similar and parallel results.
All right, thank you. And I think we have time for one more question. And the second question I have for you, isn't demodulation only good for early stage fault detection?
We've had this issue even with some of our own analysts because again, there's kind of a technical associates vibration institute. I think we have historically taught that these tools are only useful in very early stage bearing detection. Every one of the examples I gave you was late stage bearing detection. So what we find in particular with this detection methodology is that it finds it early and it tracks it late. So it has taken kind of a culture change even within my own core of analysts to make sure that they understand that they need to be paying attention to this both early and late, because it just works differently than those legacy demodulation methods. And as the fault moves into kind of the machine motion stages of those faults, sometimes impacting will reduce, but oftentimes it won't. And again, you saw every one of those cases where they were late stage faults and we were getting significant impacting. So I think that that's kind of a thing of the past, and we take it very seriously, and we try and take it more seriously every day. And as I mentioned at the beginning of the speech, when we have slow speed machines, we have found probably at least 30% of the time the impacting is the only indication we ever get. If we get to failure and we go and post look at the data, impacting is often trending early and we never see any changes in the regular data. So we have become much more dependent on impacting our impact tool, as well as thoughtful and paying attention to the data that comes from it.
All right. Well, Stephen, thank you so much for your time today. Thank you for an amazing presentation. As a quick FYI to everyone, when you exit GoToWebinar, there will be a window that pops up with a very short 30-second survey. We would really appreciate your feedback on today's session, and thank you everyone for joining today.
Thank you, everybody.